Okay, so right. Okay, so let me take a tangent vector here, or let me take two tangent vectors, say xi eta. These are tangent vector. So let me call this space X. So, well, so let me take two tangent vectors at ut of X. Okay. And let me take a tangent vector. So xi is of the form, say, so what will it, so it will be of the form v comma say del t, right? Okay, where v belongs to u perp, right? Because what is, it's the tangent space of the unit tangent sphere cross the tangent space of 0 infinity, right? So the tangent space of the unit tangent sphere at u is u perp, right?
Yes,
Yes,
yes, yes, sir.
this is
Yes.
the tangent space at u of TP1 HN.
Hmm.
Okay,
Hmm. Yes.
and if I take eta to be say uh, zero comma del t, okay, then what is g tilde first of xi comma xi? Let's look at this first. So this is going to be phi upper star g of xi xi. So this is g of d phi xi, d phi xi. Right? Okay. And
Yes.
so what is g of this? This is what is d phi xi first of all. So, so I mean, this is your picture. This is u, and this is gamma t. Okay, this is gamma prime. This is gamma t. And I'm taking a tangent vector to u. This is v. Okay. So then I'm looking at basically this point here. Right. So xi I can write as basically ddt of well, okay, fine. Let me put a lambda here. I put a lambda, doesn't matter. Okay, so it's ddt of u plus, okay, fine. Take delta less. Of u plus sv, comma, so this should pass through t, right? So yeah, t plus lambda s, right? Okay. Okay, actually, fine. Let me get rid of this lambda for the moment. Okay, fine. So let me take a 0 here. So then this is just t. Okay, this is xi, right? I can write xi like this. Yes.
Yes, sir. Yes.
I mean, well, okay, this is not a unit tangent vector, so I have to divide by norm u plus sv. Okay, fine. Then this is okay. Then this is a curve in the unit tangent sphere, right? Whose derivative at time 0 is v. And this is derivative is 0. This is constant. T is fixed. Yeah. So therefore, d phi xi, this will be dds at s equal to 0 of xp of t of u plus s v over norm u plus sv, right? Is this okay?
Yes, sir.
So what is this? This is going to be the derivative of the exponential at p, d of xp at the point tu of tv. Is this clear? Right? Okay, so there's this, and yeah, that's it. It's just this, right? Is this clear?
Yes, sir. This
Yeah,
is
so
fine.
therefore, this is fine. So this, so this is my j of t, right? This is my
Mhm.
j of,
Right.
right? So therefore, norm, so therefore, g tilde of xi xi, this is equal to norm d phi xi squared, which is equal to norm jt squared, which is equal to norm v squared sin h squared t, right? Yes.
Yes, sir. Yes.
So what is this norm v squared? On the other hand, this is equal to my d theta squared of xi xi, right?
Yes. Right.
Right. This is equal to d theta squared of xi xi. Okay. Now, what is g tilde of eta? Eta. So eta was 0 comma del del t, right? So this is going to be norm of dd s at s equal to 0 of uh, exp of t times, oh sorry, t plus s, right? U. Is this clear? Right? Because eta is DDS at s equal to 0 of 0 t plus s, right? Is that clear? Yes?
Yes, sir.
Okay, so this is equal to, so d phi eta is DDS at s equal to 0 of x p s plus t t plus s u, right? So this is nothing but gamma prime t, right? Yes, this is just gamma prime t. Is this clear? Yes.
Yes, sir.
Yes.
Yes, sir. This is it. Right.
This is a DDS of gamma t plus s, right? This
Yes,
is just
yes.
gamma. So this is gamma prime t, right? So this is 1, which is the same as I mean dt squared of eta. And finally, let's look at g tilde of xi eta. So this is going to be g of d phi xi, d phi eta. So this is going to be inner product of d phi xi, d phi eta. So this is inner product of jt gamma prime t, right?
And this is 0.
This is 0 because j is a perpendicular vector,
Right.
Jacobi,
Jacob.
right? So therefore, what do we get? Finally, this implies what? That basically any tangent vector can be written as a linear combination of these two, right? These xi and eta, right? Yeah.
Yes.
Right. Any tangent vector is of this form. So if I take basically I mean, if I take some mu equal to xi plus lambda eta, right? Then what is g tilde of mu? This is g tilde of xi plus lambda eta, xi plus lambda eta. Okay, so here lambda belongs to R. And so this is bilinear. So this is g tilde xi plus 2 lambda g tilde xi eta plus lambda squared g tilde eta. So this is just sin h squared t d theta squared of xi plus dt squared of lambda eta, right? Okay. In other words, what this leads is this following polar coordinate expression for the metric g tilde is, I can write it as dt squared plus sin h squared t d theta squared. Is this clear?
Yes, sir.
Yes, sir.
Okay, so this is the expression in polar coordinates. So this is what's called a warp product metric. So it's a metric on a product space. In this case, the product is of the sphere with the interval Sn minus 1 cross 0 infinity. And what you're doing is basically you're warping the spheres. The metric, this d theta squared is the metric on the sphere. You're multiplying this by the function sin h squared t. Okay, this dt squared is in the perpendicular direction, in the radial direction. And so this is the radial coordinate and this is the polar coordinate, the spherical coordinate, the angular coordinate, right? So in the angular direction, you're multiplying the spheres by sin h squared t. Does this make sense? Okay.
Yes.
So it sort of looks like this, basically, that if these are your cross sections, these are your spheres are getting larger exponentially. Do you understand? Basically, this is equal to Sn minus 1 cross singleton t. Okay, so that's why it's called a warp product metric. You see, you're warping these fibers. I mean, these are fibers over a base, right? You have a base which is 0 infinity. And this is Sn minus 1 cross 0 infinity. Okay, right? So this has so this thing has so this is your pi inverse of t, right? You see the picture? Yes.
Yes.
And the fibers are growing exponentially, right? So I'm multiplying the metric by sin h squared t. That means I'm multiplying the spherical metric by sin h, the norm by sin h t. So distances get multiplied by sin h t. So therefore, this has this is a sphere. I mean, pi inverse t is basically a sphere of radius sin ht, right? This is isometric too. Sphere, round sphere of radius sin ht. Okay, so these spheres are growing exponentially. You see, what is the difference between this and Euclidean space? If I did the same computations in Euclidean space, instead of sin ht squared, I would get basically t squared, which is the solution to the differential equation. My Jacobi field, instead of being sin ht, r sin ht, it would be r times t. It would be a linear Jacobi field, right? Where the Jacobi equation will tell you that the norm of the Jacobi field satisfies norm j double prime equal to 0. So, right? Yes? Do you understand? So then in Euclidean space, my spheres, they grow linearly. but in hyperbolic space, my spheres grow exponentially. Do you understand the difference? Yes?
Sir, is it in some sense you're
Yes.
saying that that coupling is that there is no coupling of the volume, Riemannian volume here? That's what you're saying?
Uh,
I mean, like in case of the Euclidean space, we know that if we look at say a sphere or a ball and then we dilate it, and then if we look at the ratio of the volume, it does not depend on the radius. Just it's a dimensional constant.
right, right.
But
Yeah,
here
that's-
it's growing exponentially. Yeah.
Here it's growing exponentially, right? And here you don't have dilations, right? You don't have dilations.
Yes. Yes.
See, what happens if I multiply the t coordinate by k, then this will become sin h squared kt, right? That is not k times sin h squared t or k squared times sin h squared t, right?
Exactly. Exactly.
In Euclidean space, the k would come out, you see? So you would get a scaling of the metric. Here you don't have a
that's what I'm-
scaling by, you don't have a dilation here. You don't have a dilation here. Right? Does that make sense?
Yes. Yes.
Okay. So is the picture clear? You get this warp product metric on the in hyperbolic space. Okay, so this is useful for calculation sometimes. And yeah. Okay, is this all right? So I just wanted to give you an application of this lemma that we proved about Jacobi fields in constant curvature. It also leads to an explicit formula for the metric, the hyperbolic metric, as a warp product. Okay. Yeah, is this picture makes sense? Okay, so it has a
Yes.
singularity. There's a singularity at the origin, of course. These curves, they at the origin it shrinks to a point, right? So
So just one question, like the way we have seen here the polar decomposition.
yes,
So are we like in the more general symmetric space point of view, is it just the k quotient term cross a plus that direct product, that product?
sorry. Yeah, so say that again.
I mean, like here in the real hyperbolic space, we are getting say Sn minus one cross open zero infinity, this sort of a polar decomposition. So in the
Right.
more general, say non-compact symmetric space of non-compact type, and say rank one for the time being,
Right.
is it similar to that k quotient m cross a plus? I mean, k is the maximal compact subgroup, n is the
Yeah.
centralizer, and a plus the positive Weyl chamber. Is it that concrete here?
Yeah. It's a k mod m cross a
A
plus.
plus.
Or cross, I mean, yeah. Well, yeah, that would be in a general symmetry. But in rank one is just k mod m cross zero infinity. Right.
Yes,
And this
yes.
is identified with this is identified with Sn minus one again. Okay, it's still Sn
Yeah.
minus one.
SON quotient SON minus one. Yes.
It's still Sn minus one. Okay. Okay, or maybe I should write it in a more symmetric way. Yeah, A, if I think of A as a multiplicative group, then this is zero infinity, right? Okay.
Yes, sir. Rank one.
Yeah, then this is just in rank one. Just rank one. Rank ones are negatively curved, so we have this. Well, okay. See, this this polar decomposition that this works for any Hadamard manifold. If X is a Hadamard manifold, that means it satisfies the hypothesis of the Cartan and Hadamard theorem. So it's complete, simply connected, and non-positively curved. So section curvature less than or equal to 0. Okay. Then we know by the Cartan-Hadamard theorem that this Sn minus 1 cross 0 infinity maps to x minus p. This is a diffeomorphism always, right? Given by the exponential map, right? It's just u comma t goes to xp of tu. Right? Where you identify u as a unit tangent vector, the unit tangent sphere at x you identify with Sn minus 1. Okay. So x minus p is always Sn minus 1 cross 0 infinity. So you have polar coordinates always in any Hadamard manifold. Doesn't need to be symmetric space or anything. All right. It's always, even so, this works for higher rank as well. Higher rank symmetric spaces are still non-positively curved. Okay.
Okay.
Yes, Utsham. All right. So this is purely geometric. You don't need any algebra, nothing. This is just the Cartan-Hadamard theorem, nothing else. This is just the Cartan-Hadamard theorem. Right?
Right, right.
Okay. Yeah. Oh, so I made a mistake here. This will be G mod K, well, minus a point P, minus the origin. Okay.
Right.
This is not the whole space. This is. So actually what we're doing here is really the Cartan decomposition of the space. This polar coordinates, that corresponds to the Cartan decomposition. G equal to KAK. Right?
But in order to get the uniqueness, we need to get rid of the m orbit. So K quotient.
Right. I mean, that's when I quotient by K, then yeah, then I'll get K mod M cross A. So, but this is the Cartan decomposition, right? KAK.
Right.
Right. So yeah. But the point is that we can calculate the metric explicitly here. Okay, using Jacobi fields, we can calculate the metric explicitly in this polar coordinates. So we have, just like you calculate the volume element in polar coordinates in your calculus, high school calculus. You do volume, volume area integrals in polar coordinates is r dr d theta, right? That's the volume element. That's in Euclidean in the plane, and similarly here you can calculate the volume element in polar coordinates, and that makes integrals of very easy to calculate. You see, so I can calculate the integral of any radial function using this. Do you understand?
Yeah, because we have written it in terms of like the radial part and
Yeah,
the.
so I mean, this will tell us what the volume element is, right? What is the volume element? Volume element means basically if I take so if say omega is equal to volume element of the sphere of Sn minus 1, okay, right? Then omega tilde, this is the volume element of Sn minus 1 cross 0 infinity with the metric G tilde, right? Okay, this is Sn minus 1 with the metric d theta squared. Okay, fine. Then this will be what? This will be just so what should it be? So basically, it's going to be some function times so f of t u or f of ut into d theta squared wedge dt, right? Because this is a top degree form, right? And so what will be an orthonormal basis here? So, I mean, omega of an orthonormal basis has to be 1, right?
Yeah.
Right. So my orthonormal basis, basically I take an orthonormal basis for the sphere and I take del del t for the r direction. That will give me a basis, right, for this, right? So yes, is that clear? So if
the tangent space for product is the direct sum of the tangent spaces.
right. So if I take, let's say, v1 to vn minus 1, this is an orthonormal basis of u perp with the metric d theta squared. Okay, fine. Then at ut, what will my orthonormal basis be? Basically, these have d theta squared length 1. So in G tilde, these will have d theta length, these will have G tilde length sine ht, right? So I have to divide by sine ht. Yes?
Yes.
So v1 by sine ht comma 0 up to vn minus 1 by sine ht comma 0 comma del del t, right? This is an orthonormal basis of the tangent space to at ut to x with the metric G tilde, right? Yes?
Yes.
Now I want omega tilde of this to be 1, right? Okay, so omega tilde of these v1 over sine ht 0 up to vn minus 1 over sine ht 0 0 del del t. So this is going to be 1 and this is going to be f of ut, and then basically this 1 over sine ht will come out to the power 1 over to the power n minus 1, right? 1 over sine ht power n minus 1. Yes? Okay.
Yes.
And then what will happen is I'll get d theta squared applied to v1 to vn minus 1 times del del dt applied to del del t. So that will be 1, right? So that means therefore that f of ut is sine ht power n minus 1. So it doesn't depend on u. Okay. So this is the volume element. This is the volume element. Okay, so in polar coordinates, the volume element in polar coordinates. So for Hn, the volume element in polar coordinates is omega tilde equal to sin h t power n minus 1 omega tilde, sorry, omega wedge dt. Okay. Is this clear?
Yes.
So if I take a function f is in L1 of Hn, all right, what is the integral of f dvol Hn over Hn? So if I use polar coordinates, right, then this becomes the integral from 0 to infinity of the integral over Sn minus 1. F becomes a function of ut, right? Yes?
Yes.
And then I have d omega. This is the volume element of Sn minus 1, the round sphere. And then outside I get this sin h t power n minus 1. Dt, right? Okay, so this gives us an explicit way to calculate integrals, right? Is it clear?
Yes.
So, and if f is radial, that means it is constant on spheres around P. Okay, so then so let me write the radial coordinate as r. So f of ur is independent of u, sorry. So this is just some function f of r, right? And so then the integral of f over Hn dvol is just the integral 0 to infinity f of r sin h r to the n minus 1 dr, well, into the volume of the Sn minus 1, volume of Sn. So this is some constant which depends on n. That's all, just some constant, right? Is this clear?
Yes.
Okay, so you can see that a radial function will be L1 if it has enough exponential decay, right? It has to decay exponentially fast enough, right?
Yes. Yes.